so I'll be trying to solve this problem. Okay, I guess. Okay, so what is this problem, right? Maybe you should watch this first. This sort of like explains how to solve it. Yeah, anyway, so the idea is, let's just like take an example and sort of like look through it. Okay, so you're given an undirected graph where each edge has one of two colors, it's either black or it's red, and your task is to assign a real number to each node so that for each black edge, the sum of values at its endpoints is 1. For each red edge, the sum of values at its endpoints is 2, right? Okay, so let's sort of draw that out. So let's say you have a black edge like this, right? And let's say you want to assign like, I don't know, 0.3 here. That means you have to assign 0.7 here, such that this sum here is 1, right? So summing those up is 1. On the other side, if you have two nodes like that, just sort of connect them together, you can do, you assign like 0.3 here, you'd have to assign 0.7 here, such that when you sum them up, you get 2. Okay. This seems fine. Now, the idea is, so you want to do this, but then the sum of the absolute values of all assigned numbers is the smallest possible. Which means, let's say, so you assigned like some x1 to this, and then some x2 to this one. So you want to do, if you sum over, right, all of the xi's, you wanna minimize this. Right, so the way you do this, it's actually just a DFS, and you keep a sense of some sort of an equation as you go through. So right, let's take this example here. Right. Right, you can go from 1 to 2. You can go from 2 to 3. You can go from 1 to 3. And you can go from 3 to 4. Go from 3 to 4. Okay. So the way you do this is you actually solve it symbolically. So you think to yourself, okay, let's sort of try to assign like some sort of x1 to this. And actually, the way you'll be looking at it is you assign some x to this, and you think of it as a linear function, right? Maybe this is like the hardest part of actually realizing why you would want to do that. Well, it's because whenever you go to a neighbor, you can actually see how these A1 and B1 switch up, right? So whenever you go to A2, for example, right, you want this to sort of be negative A1x plus some s minus b1. Now this s is 1 in case of this sort of edge, and then this s is 2 in case you have the red edge, right? So now you can sort of see this as a2 and then x plus b2, right? So those are sort of the constraints you set. So you can see that a1 always, so the a in this equation sort of always flips whenever you go to a neighbor, and then b2 actually ends up getting high or low values. It sort of depends a lot. b2 can grow quite a lot. Just take yourself an example and you'd see that it can grow. Right, anyways, now if you look at this, if we keep on going, let's say our DFS first goes here, and then our DFS would go here, we'd get an A3x plus B3. But then you know you would have visited this. So imagine the spanning tree of the DFS, right? You know you would have visited this. So whenever you go back here, so this is what I've written in the code, right? In case you visited your neighbor, look at the constraints of the neighbor, right? Looking at the constraints of the neighbor, this is essentially you've created a cycle. And now you know that for this to be possible, it must be that this equation is satisfied. Now you can see there are multiple cases here. If A1 is A3, then these one cancel out, which means either you have B1 the same as B3, in which case you impose no additional constraints. If B1 is different than B3, then it's absolutely impossible to satisfy this particular connected component. Now, if A1 isn't A3, you can see that you can actually determine the value of X by doing B3 minus B1, right, which is this one, B3 minus B1, and then you'd have to divide that by, I guess, A1 minus A3, right? So you get a precise value for X. And then you sort of, like, you look at these cases, then you can also like propagate here and get your next value for A4X plus B4, right? So there's like multiple cases that the DFS can end up with, right? So you propagate symbolically through the graph, and then if you have a cycle, you look at that AI/BI, and you have multiple options. Either it doesn't impose a constraint, so you just continue iterating. It precisely defines X, and you continue. And you can see that if you have precisely defined X and you find another cycle, like we do here, right? So we find another cycle. In case HCV means we already sort of had a current value, right? Then in case this new current value isn't the same as our new value, in that case you just return false. Returning false means it's sort of impossible, right? So if R is false, you return false. Otherwise, if R is true, you sort of like keep on going. So if you can go through all of them, you return true. Okay, right? So otherwise, in case either you don't have a current value or the current value is the same as the new value and you haven't returned from here, then you say that you have a current value and your current value is the one you just computed, right? So you can actually compute X. So the DFS either will not impose a constraint, it will precisely define X and you can sort of go on, or you will determine it's actually impossible to fulfill the connected component. Out of the DFS, you may come out with either a precise X, right? Because all of these equations, all of the cycles checked out to the same X. The fact that it's impossible to get an X, or you can also you don't come up with an X, but you have now determined all of the constraints, right? So for example, if you ended up with this case here, A1 was the same as A3 and B1 was the same as B3, which means you didn't impose any additional constraints, then that means you now have AI/BI. So you have sort of so this C here stands for constraints. So this is the set of all of your constraints. And you can think of this set as sort of, okay, kind of now, so given an X, you can actually determine all of the values, right? So let's say take some X, which is a real number, and if you want to determine the absolute value, right, of all assigned numbers, what's that, right? Well, it's a function of X that sort of goes through your entire set. So it also depends on your set of constraints here, of course. So that's just doing AIX plus BI, right? For all of these different things. Now what they do in the editorial is, okay, you're just trying to minimize this. They're doing something like this. So you know that AI is either -1 or 1 because you must only ever flip it, right? You know it's either -1 or 1 because you must only ever flip it. You're gonna factor out AI forcefully, and you're gonna be writing it as such. You're gonna define this as some sort of quantity called Ri. You can see now we can like ignore the AI. Right, so you're gonna do this. Now if you know this, if you've solved problems before, this means that x minimizes, x is median of Ri's, right? So you sort of know what x is now. Okay, so these are sort of all of the cases. Maybe I went through them a little too fast, but anyways, just make sure you read the problem and whatever. Just try, just look at the editorial. It's pretty well made. But anyways, let's see if we can sort of solve this. So this is right. So you can see this is how we're computing like the constraints of our friends. Let's see what happens here, right? So you usually start out with 1 and 0, so you're gonna flip this to -1 and then 1, right? In case, wait, so which edge is like first? God only knows, because you may like go to the other one first. Okay, this edge is first because we keep the order. Okay. So this is gonna be 1 0, is gonna be -1 1, and then you're gonna end up here with I don't know then 1, and then you do 2 -1, so you get to 1 again. So this one would like to induce a -1. this one would like to impose negative 1, 1. So you'd have something like x plus 0 would be negative x plus 1, I guess. Yeah, so you get that x is a half, right? Um, no one cares about initializing this. Okay, include a factor. Guess I'm missing one of these. Let's see. The current value. Stuffed in. We don't use vector double. When doing DFS, we need to prop. Constraints. You also want to do that. Just saying no. Why are we saying no, dude? So HCV was 1, current value was 0.5, and new value was 0.5. what's going on, dude? Current value minus new value should be essentially 0. Okay, that's not how we propagate. So what does propagating mean? It means you need constraints. So you need constraints. You need to do things like constraints. Constraints at what? Otherwise, you're gonna need to take the median of this array that we talked about here and just try to sort of propagate that one, right? So what do you want to do? You want to do some sort of like special median array, right? Let's just like take this as we go, I guess. So you need vector of double median. So DFS is gonna take this here. So every single time you visit here, constraints are already set for me. You want to do median and you want to push back negative b, divide that by a, right? So you want to push out this quantity, which is the Ri. It's the R quantity. Right, so if you made it here, this means you can actually, so you can sort taking a median. If your array looks like this or your array looks like this, if you take the size, divide that by 2, you end up here. If you take the size and you divide that by 2, you like 4, you divide that by 2, you end up on this one. Otherwise, here you end up precisely on the one that's precisely on the middle. Here you end up on the one that's like sort of to the right. So the value is the median that size, divide that by 2. Right, so this case comes sort of like, okay, how about if, right, so try to think of the case, right? The case is you don't have this red edge here. So from 1 to 3, you don't have an edge. right? You're gonna end up with these constraints, but then you're gonna do, so here I guess you're gonna end up with -1 and 0. So this is gonna be your A, this is gonna be your B. So what are your R's, right? It's like -b whatever, right? -b divided by I, that's 1. So b, you take that, you divide by that amount, so it's like 0, right? So 0, 0, -1, and then 1. So taking the median is that component right there. So right, so your x is actually 1, which is well, yes, right? So what do you want to do here? You want to do yes, and then you'd like to do okay, I guess we're gonna be staying in queue for a longer time. I don't know, dude. Probably not a lot of people. I like, how does the queue work, right? How long is this gonna stay in queue before it runs, dude? I guess I don't have the tests myself, so I can't run it. Who knows, man? How many people even solve this stuff? Not a lot, I guess. Yeah, now we're just waiting for the queue. Whew. Yeah, I guess I'll be back when we actually get something.